Hello and welcome back. I'm Professor Jim Caffey, and this is going to be Chapter 8 in our OpenStax Astronomy textbook. And Chapter 8 is on the Earth as we know it as a planet. And we use the Earth to compare other planets to what we know best, our own home planet. Here we have a volcano seen in 2006 by the space station, and this is up in the Aleutian Islands off Alaska, and there's a lot of these volcanoes up there along the Pacific Ring of Fire. One of the most famous pictures ever taken was of the Earth when the Apollo 17 astronauts were coming back. Maybe the last Apollo mission. So the inside of our Earth, we believe to have these different layers, and the least dense layer is up at the top. The very dense layer is at the bottom in the middle. So we have a core, and then another core that is liquid core, and generates our magnetic field. And then we have a thick mantle and a thin crust. So here we can see the fault lines and patterns that I was telling you about. We go over here to the Aleutians, tag off the Aleutians, and we go down to all the way to Australia and New Zealand. We can see that that forms an arc right there. We have a magnetosphere, like I said a minute ago, due to our inner, due to the outermost core, the liquid part, not quite as dense as the iron in the middle. But we do have a magnetic field. We've mapped it out pretty well, but even still today we can find some improvements to making this a model. Igneous rock means volcanic, and so it comes from lava flows, basaltic eruptions of basalt, and those can go very fast into a neighboring town. So here are the continental plates. See that the one nearest us, even to me in Missouri, I have my own little plate in the New Madrid Fault. But we see the North American plate here and the Pacific part of the Pacific plate over here coming together to form the San Andreas Fault. Well, this man didn't live very long. He's only 50 years old. Alfred Wegener. Wegener proposed a scientific theory for the slow shifting of continents. So this is Wegener that did this. In this model, we can see a rift zone, and we can see a subduction zone down here. This is where the magma can come together with lesser rock and cooler rock to make it even more explosive coming out. So here's a really nice shot of the San Andreas Fault going through California. I have no doubt some of you have seen it for your own self. I don't remember I did. We of course have mountains on the Earth, and we have an atmosphere. So our atmosphere starts down here at the bottom where we live, the troposphere right there. Above that a little bit, it gets a little bit cooler. You get water vapor clouds, and then we go up into the stratosphere, and that's really as high as we go in an airplane. Military can go higher, of course, but and our space station is about 265 miles above the Earth right now. I think hurricanes look a lot like our spiral galaxies do. And for that reason, I find them very beautiful in nature. Of course, one of my schools was in Florida, and they had to evacuate for a week during the first week of classes. So, tough stuff to deal with. So we have an ice age in the northern hemisphere. You see all the ice at the North Pole here. And this is indicated back in the days when glaciers were overwhelming this whole area. And here you see a fossil of a stromatolite. Stromatolite, I can get that right. And it's basically a polished cross-section of a very ancient, simple form of life that was found more than 3 billion years ago. And then we also know how the greenhouse effect works. Just like if you don't want to leave a baby in a hot car, even for 5 minutes running, because that can really mess up a child and kill it. So we have that going on here, and it gets warmer and warmer. So a lot of evidence mounting up for a lot of this. But this greenhouse effect goes on a daily basis. It's not really accumulated too much. What does accumulate is the increase of atmospheric carbon dioxide. This goes up here to like 400. We hit 400 a couple of years ago, and that was what the Paris Accords said would be the no point of return. And I think the last number I saw was 409. So, wow. Here's an impact crater. This one's in Nigeria. Around the circle here. We actually have, here in Missouri, where I am, we have a series of 7 or 8 of these impact craters going up and down Interstate 44 from Tulsa, Oklahoma City, to Springfield, where I am, St. Louis, up there. What happens if a comet fragment explodes over your head? You get this. So in 1910, we had the Tunguska explosion. Theories go back and forth if it was a comet, if it was an asteroid. But just a small fragment of a space rock can just obliterate damage. This impact in Siberia set off fire blazes in London. Pretty big deal. And all those trees were strung out in a radial pattern all over the place to show the point of actual impact. Now, I'm sure most of you have already been a meteor crater in Arizona. If you have not been, you should go. I will make it something that you can do for your last lab. I've been there. It's fascinating. I got a VIP tour. Well, what killed the dinosaurs? We think it's impact of an asteroid here in Chicxulub crater in the Yucatan Peninsula. We astronomers get used to saying those weird words altogether. Chicxulub, Yucatan Peninsula. And that's where it happened 65 million years ago. Alright guys, thank you for joining me for Chapter 8. We'll be back shortly with Chapter 9. Thank you.